Welcome back, folks. In this video, we'll start with an intro to our next unit, which is kinematics. So in physics, the study of moving objects can be broken into two fields. We will look into both of these fields. One of them is kinematics, and the other one is dynamics. Okay, kinematics is the study of how things move: speed, velocity, acceleration. Dynamics is the study of why things move: forces. We push on things with force and we change the motion of things. Okay, so here are three different things that we all know that they move. I'm going to draw them in a special way, though. I'm going to draw them as an arrow because that is what we use to represent a vector quantity. And would you believe that if you Google the speed of a snail, that speed of a snail tells us, or Google tells us, that it's 48 meters per hour? Okay, this is a Lambo, and I'm just going to estimate that a Lambo can travel 350 kilometers per hour. Okay, the next thing that we'll look at is the International Space Station, and I'm going to draw the direction of travel for the International Space Station as a dot or an X, and those dots will come into play in later physics classes. That dot is representing vector that's coming towards you or out of the page. Okay, and that X, that is representing a vector going into the page. Really, you can think of those dot and X as an arrow. And if you think of an arrow with feathers at the end of it, if you're standing behind it and it's traveling away from you, you'd look at that arrow and you'd see an X for the arrow. However, if in the other case, if an arrow is coming towards you and you're looking at the tip of that arrow, all you'd see is little points. So that would be an arrow that's coming towards you. Okay, so the speed of the International Space Station is, it's moving at about 7.66 kilometers every second. Okay, so in each one of these cases, it's just some length divided by some amount of time. Okay, so and that's what we'll end up getting to when we're talking about speed and velocity. Okay, this next section here, I've just gone ahead and filled them in. This is just neat to know, I think. There are only 7 base units when it comes to the metric system. Okay, so the 7 base units are on the screen. We've got time in seconds, mass in kilograms. In chemistry, we talk about the amount of substance with units of the mole. Light intensity, we talk about in terms of candelas. Temperature, that K stands for Kelvin. Okay, electric current, the A stands for ampere. And then length, we talk about in base units of the meter. Okay, so the 3 that I've highlighted are going to pertain to this unit, and just some derived units that we will use these base units with are velocity. So we'll talk about velocity in terms of meters per second. We're really just combining together those base units. Okay, acceleration, we'll talk about how objects accelerate, and we talk about those in units of meters per second squared. Okay, and the last one I'll put on here, this is one that pertains to dynamics and forces. When we get to talking about dynamics or forces, they are made up of kilograms times meter per second squared. This is also known as a Newton, named after that famous scientist, Sir Isaac Newton. Okay, so we'll get to those as we go throughout our year here. Okay, so next we'll talk about the difference between scalars and vectors. Okay, so scalar quantities are things that have magnitude only. Magnitude is just a special name for size. Okay, so those are quantities that just have a magnitude. Okay, whereas vectors, those are described with both a magnitude and a direction. Okay, vectors are quantities that we always draw those as an arrow. And I want to stress this right off the hop. We're not going to draw vectors as a line. We're going to make sure that we put arrowheads on there. Okay, so looking at examples of each of these types of quantities, things that do not need direction are scalars. Those are things like temperature. Okay, and we'll talk about temperature later in units of degrees Celsius or Kelvin. Okay, we'll talk about those more later. Okay, time in seconds. Time cannot have a direction. Okay, mass is another example of something that is a scalar quantity. Okay, as opposed to vectors, when we start talking about things that have direction, things like velocity. Velocity, we'll talk about it in units of meters per second. Okay, forces as an example, like, hey, 12 newtons, or we would use a negative sign if we're pulling in the opposite direction. And sorry, some examples of velocity here. In terms of direction, we usually use things like a plus, like something's moving at 18 meters per second, or we'll say, hey, something's traveling at like 6 kilometers per hour to the south. That's another way that we will indicate direction. Okay, small thing just to separate the ideas between scalars and vectors. Okay. Moving on, we'll talk about the difference between position, distance, and displacement. These are three important words when we're talking about where things are. Okay, so when we're talking about the position of something, it is a vector describing where an object is. Where an object is. Okay, and in this diagram over at the left, at the left, this position A, that's just talking about, hey, that's just a vector, just describing where it is relative to some reference point. Okay, so distance, if we look at distance, then distance is, this is a scalar quantity that describes, scalar describing the length of a path an object takes. Okay, so we've all used the word distance before. Hey, how far did you walk? Well, I walked 300 meters to school. Or how far away is Kelowna? We talk about it being 70 kilometers away or so. Okay, so we just talk about the number part, which is distance. It's just a scalar. Okay, so displacement, however, that is a vector quantity describing the change in position. Okay, so if your position changes, you draw a vector from where an object starts to where an object ends up, and that vector quantity would be your displacement. And I'll kind of highlight some things on here, like the word displacement in that diagram. Okay, I'm also going to just highlight, hey, position is a vector, distance is a scalar, displacement is a vector. We're going to have lots of practice with these words and come to understand what they mean in some good detail. Okay, so a couple of examples here, the difference between distance and displacement. Okay, so if a car drives 3.2 kilometers east before turning around and driving 5 kilometers west, what's the car's distance and displacement? Now, first, I just want to comment on northeast, southwest. Never eat shredded wheat is the acronym that or the mnemonic that I use to remember it. We're going to need to know our Cartesian coordinates so that we can talk about things in a unified manner. Okay, so if I draw a little diagram here, if we have a car that drives 3.2 kilometers to the east, okay, and then it turns around and drives 5.4 kilometers to the west, what's the car's distance? Well, distance, we're just going to add them up, right? What's the total distance that something travels? We're just going to add up how far they've gone, or in this case, 8.6 kilometers. Okay, so in the for displacement, though, we want to look at, hey, where is an object now compared to where it started? So this I'm going to put as a D with a little arrow hat on there. And sorry, folks, I should have also put up here, beside displacement, we commonly use D with a little arrow hat to represent a vector quantity. So I'll just show that as our displacement being that D. So in this case, if we're looking to solve part B, finding the displacement, really we're looking at, hey, how far or how long is that vector going to be? So that'll be 5.4 minus 3.2, or our displacement is 2.2 kilometers. And with displacement, we always have to indicate a direction. So which direction is that vector pointing? Well, it's pointing west. Okay, to indicate direction with Cartesian coordinates, we'll usually use square brackets, like you can see on the page. So that question is done. Okay, so next, if we have a question where we have a couple of different directions involved, we're going to need to use some trigonometry. So if I kind of talk through this and talk and draw as I go, if we're going to go from Penhai to the Sicamous by walking 700 meters north and then 1.2 kilometers west. Now 1.2 kilometers, if I'm going to put vectors on the same vector diagram, they have to be in the same units. So I'll change that to 1200 meters. Okay, and then my part A is what is the total distance walked. So part A is just going to be 700 plus 1200, or this person has walked 1900 meters. Okay, part B, where you're looking at your displacement, that gets a little trickier. So now we're looking at displacement as being a vector that looks like so. And within this diagram, which is a right angle, we're going to have to employ our knowledge of Pythagorean theorem to solve for what our displacement will be. Okay, and in this case, we can find the magnitude by doing 700 squared plus 1200 squared is equal to displacement squared. Okay. And then if I plug and chug that, we'll find that our displacement squared is 193,000,000. Really, really big number. Okay. Then to find the magnitude, we'll have to take the square root of both sides, and we find that the length of that displacement vector will be 1389.2 meters. Okay, and then I'm just going to ask the question, does that make sense? Like, does that number fit on this diagram? And I know my diagram's not to scale, but I can look at that and think, okay, well, my hypotenuse, which is the displacement vector, it has to be the longest side. So yeah, that makes sense. It's a little bit more than 1200, definitely bigger than 700. Yeah, so that kind of checks out in my mind. Okay, next, if we want to find the angle, which we have to talk about the angle that our displacement vector is pointing, we are going to use a tangent ratio for that. Okay, so from trigonometry, we know that the tangent of an angle is equal to the opposite over the adjacent. In our case, the opposite side to theta is 1200, and the adjacent side is the 700. Adjacent just means beside. So we'll find that our tangent theta is equal to 1.7. Okay, and then if we do the inverse tan of both sides, the inverse tangent sort of undoes that tangent that's attached to the theta. So using our calculator, if we do the inverse tan of 1.7, we should find that our angle is, and I'm going to round it to from 59.7 to 60 degrees. Okay, so now how we state this answer is kind of tricky, kind of neat though, because this will be new. We say that our size of our vector is 1389.2 meters, and then to indicate direction, this angle of 60 degrees in here, we need to reference either our northerly or our westerly coordinate system. So what we would say here is, hey, if we start off pointing to the north, we need to go 60 degrees west of that. So we need to go 60 degrees west of north, and that is how we state our angle or our direction when it comes to using our Cartesian coordinate plane. Okay, so there's a couple of examples. There are some examples to try on your worksheet, and thanks, and we'll see you again soon.